Hello chemistry friends! Get excited because today we're going to learn how to make a graph. After our lessons today, you're going to have some tremendous graph creating skills. So we're going to talk about a few strategies that you want to incorporate after you've done a scientific experiment and collected quantitative data. Today we're going to make a line graph. That means you've collected data from a lab that is numerical. And ultimately what we want to do is figure out the relationship between the independent and dependent variable. So let's talk about a few things that you want to include on your graph. The very first thing that you always want to include is a title. Now, the title shouldn't be something like Tiffany's experiment. The title should indicate what was the experiment all about. In other words, what was the independent and dependent variable? For instance, if I was boiling water and I was heating it gently, and over time I was trying to see how the temperature increased, I might want to use a title like Temperature of Water versus Time. Okay? So in your title, make sure you're indicating to the reader what this experiment was all about. So we're going to indicate up here that we always want to include a title. Now, you've got two variables in your experiment. You've got an independent variable and a dependent variable. Traditionally, down on the x-axis, that's the horizontal, that's where we're going to be plotting our independent variable. Over on the y-axis, we're going to be plotting our dependent variable. One thing I want to make sure you understand, if you're ever doing an experiment that involves time, traditionally, time is always plotted down on the x-axis. One thing you want to make sure you do as you label your axes is always include your units. Are you measuring the temperature in degrees Celsius or Fahrenheit or even Kelvin? One of the mistakes that I want you to avoid making is trying to connect your data points with a dot-to-dot graph. That's not the way we do it in science. You don't want to simply go from here to here to here to here. Okay? When we create a graph, we're looking for a line of best fit. If your line seems to be indicating a straight line, then create a straight line. Get a ruler out and very, very nicely create a nice straight line for us. So let's ignore the dot-to-dot line that I've created. I'm going to get my ruler out as best as I can, and my line might go through some of the data points, and some of the data points might not hit the line, but that's okay. What we're looking for is a trend. I want you to think about why we create a graph. During a scientific experiment, we're collecting data. After the experiment, you need to analyze and interpret the data. And ultimately what you're trying to figure out is the relationship between the independent variable and the dependent variable. That's the beauty of the graph. It's going to actually give you meaningful information about how those two variables are related. So if we look at the pink line of best fit that I've created, a scientist would say there's a positive correlation between the variable on the x-axis and the y-axis. What that means is, as your x variable is increasing, your y variable is also increasing. Now there's another type of graph. If you see a graph like this, you'll notice there's a negative correlation between the x-axis and the y-axis, which means as the x variable is increasing, the y variable appears to be decreasing. We call that a negative correlation between the two variables. The next thing that I want to teach you is one of the most difficult things that students struggle with when they're creating a graph, and that's making the increments so that you can plot your data points. So let's talk a little bit about what's important when you're creating the increments on your graph paper.
So here's a really simple scientific experiment. Let's take a plant and let's try to figure out its height after a certain number of days go by. Here's some data that we've collected. You can see that on the first day our plant started off at 8 centimeters, and by the 15th day the plant had reached a height of 70 centimeters. So the plant is definitely growing. We can do something really simple with our data to analyze it. I'm going to draw a really simple arrow showing the direction of the time increasing. Okay, and then on the other side, let's show the direction of the height increasing. So as we go down the data table, we can see an increase in the height, and as we go down the data table, we see an increase in time. That's a really simple snapshot of the relationship between the independent variable and the dependent variable. As the time is increasing, the height is increasing, and we call that a direct relationship. So let's get to the graph. A few things that we know about the graph. First of all, it's got to have a title. You can do something really simple with the independent and dependent variable like time versus height. Or you can make it sound a little bit fancier and more professional by saying the effect of time on the height of the plant. Well, down on the x-axis, we know we're supposed to be putting the independent variable, and notice we've included the units of days. And then on the y-axis, the vertical, we've got the dependent variable, which is height, and the unit for that is centimeters. Now, the hardest thing for students sometimes is figuring out what are the increments on the graph. In other words, what does each box represent? But you can't just plop down numbers wherever you want. The first thing I want to do is on our x-axis, I'm actually going to count up all the boxes that I see on the x-axis. And if we count those up, we're going to find 17 boxes. Now, as we look over at our data, for the independent variable, which is placed on the x-axis, our highest value is 15 days. That means we need to try to spread 15 days across 17 boxes. So how are we going to do that? Let's take the highest value for the data, which is 15 days, and let's divide by the number of boxes, which is 17. And what we get is kind of an ugly number. 0.7 days is one box, and we could definitely use that. We could make each box 0.7 days. That means the first box would be 0.7, the second box would be 1.4, the next box would be 2.1, and so on. But you might want to work with increments that are a little bit easier. So my advice to you is you can always round up if you want to. So that means each box would be 1 day. So now I'm going to go over and let's indicate that that very first line where we're starting, that's going to be our 0 mark. The line after that will make 1 day, then 2 days, 3, 4, 5, 6, 7, and so on. And you want to keep the increments consistent. If each box is equal to 1 day, then don't start changing it up and make a box worth 5 days. That doesn't make sense. So that's what we're going to use for our x increments. Now what about the y's? If we look at this y-axis on the vertical, I'm going to count up, and there are 20 boxes on our y-axis. And if you look at our highest value, our largest value for height is 70. That means we need to spread 70 centimeters across 20 boxes. So the best way to figure that out, let's determine the y increments by taking 70 centimeters, which is our largest value, and divide by the number of boxes, which is 20. And you come up with 3.5 centimeters per box. So you could make each box worth 3.5. It's not the prettiest number to deal with. I find that students like to round up a little bit to work with numbers that are easier. So if we rounded this box up, every single box would be equal to 4 centimeters. So again, right here is going to be our 0. The first one's going to be 4, 8, 12, 16, 20. Well, let's clean that up a little bit, and you can see what our increments might look like once we're entirely finished putting them all in. And now it's time for us to graph. So we're going to take our very first data point, and when time is 0, the height of the plant was originally 8 centimeters. Great. When the time was 3 days, we want to go all the way up to 20 centimeters. When the time is 6, we want to take that all the way up to 30, which is going to be right in between that 28 and 32. When it's 9 days, 46. When it's 12 days, we're going to go up to 56. And the last piece of data, 15, is going to be a height of about 70, if we can get that on the graph. So now we've got all our data points placed on the graph, and it's now time to draw a line. Not every graph that you make is going to be a straight line. If it looks like it's a straight line, grab a ruler, some type of straight edge, and draw the straightest line that you can. You can tell as you look at the graph from the left-hand side to the right-hand side, this line is definitely going upward. You would say that there's a positive correlation between time and height. Putting that in normal vocabulary terms that all of us can understand, as the time increases, the height increases. And again, as I mentioned before, this is called a direct relationship. So here's a few reminders that you need to remember about increments. You can take your largest value from your data and divide by the number of boxes, and that's going to help you figure out what each increment should be on your graph. Second, keep your increments consistent. Once you figure out that each box is worth, let's say, 2 days or 5 days, you got to stick with that all the way across that axis. And finally, number 3, when you're marking the increments on the graph, put the numbers next to the line and not next to the space for each individual box on the graph. Let's take a look at another experiment now. And in this situation, looking at the picture, we can see that there's a syringe and there's a gas that's trapped inside that syringe. And what we're going to do is we're going to purposely change the pressure of the gas, and we want to see how the volume is affected by that change. Here's the data that we came up with, and looking at it real quickly, I want you to try to analyze it with me. We start off at a pressure of 1, and you'll notice it's increasing as we go down the data table. Okay, so we're increasing as we go down the data table. But then look at your Y variable for volume. The highest data point is actually up here at the top, and the lowest is down here on the bottom. Our values increase as we go up the data table. As one is increasing, the other is actually decreasing, like a teeter-totter. We call this an inverse relationship. So let's get to graphing the data. We need a title. We're going to put the effective pressure on the volume of a gas. Let's label pressure, our independent variable, with units down on the bottom. On the y-axis, we've got our dependent variable, which is volume, and the unit is in milliliters. So to determine our x increments, take your highest value, 4 atmospheres, divide by the total number of boxes, which is 17. And what we're going to find out is that each box represents 0.235 atmospheres. Again, to me, that's kind of an ugly number. I always recommend you round up to make it a little bit more convenient for yourself. And this is a nice number to work with because we can proportionally think about it as, well, what if I just wanted to label every 4 boxes? Every 4 boxes means let's take 0.25, multiply by 4, and we'd realize that every 4 boxes should be labeled 1 atmosphere. So let's start at 0, and let's count over. 1, 2, 3, 4. We're going to label 1.0 right here. 1, 2, 3, 4. Let's label 2.0 atmospheres. 1, 2, 3, 4. We're going to label 3 atmospheres. 1, 2, 3, 4. 4 atmospheres. So we've got all of our increments filled out for the x-axis. How about the y-axis? The total number of boxes on the vertical is 20. The largest value for volume is 120. So we've got to take 120 milliliters and spread it evenly across 20 boxes. And this gives us a really nice number to work with. It's telling us that every single box should be a value of 6 milliliters. So as we begin, we've got 0. One box is going to be 6. The next box gives us 12. Add another 6 is going to give us 18. We've got 24, 30, and so on. Let's make that look a little bit more professional for you, and it's going to look something more like this. Take our first data point, which is 1 atmosphere on the x-axis. Let's follow that all the way up to 120. Wow, we covered that entire y-axis, didn't we? That's our first data point, way up at the top. When it's 1.5, which we understand would be right smack dab in between 1 atmosphere and 2 atmospheres, we are looking at a volume of 80. At a pressure of 2, we're looking at 60 milliliters. When we've got a pressure of 3, we're looking at 40 milliliters. And our last data point is at 4 atmospheres. Let's take it up to 30. Ask yourself, does this look like a straight line? If I were to do a straight line on this, it would definitely not go through all of these data points. What I'm thinking swoopy. I like to call this a swoopy curve. And I noticed something else about it. I noticed that as I look from left to right, that first data point is up really, really high on the graph. And then as we move toward the right, the data points start going downward. This has a downward slope. There's a negative correlation between the two variables. In other words, as one is going up, the other one is going down, which we mentioned before. So the key to drawing this line correctly is to try to draw the trend. We know it's a swoopy curve. We don't want to try to go through every single data point because we understand that this is from an experiment. This data might have some error in it. Not all the values might be perfect. And try to get the line close to all of the data points, but realize it's probably not going to go through all of it. Looking at this graph, we can tell as we go to the right on the x-axis, as our pressures are increasing, we are noticing that each time our values on the y-axis are decreasing. So we do call this an inverse relationship. As one variable increases, the other variable decreases. So here's some reminders about graphing for you. The line on a scientific graph is either a straight line or a curved or swoopy line. We call this a best fit line. We never do dot-to-dot type graphs with scientific graphs. You're looking more for a trend. If you've got a straight line, you always want to use a ruler. If it's a curved line, make it smooth. Don't try to touch all the data points, but try to get close to most of them. So here's an experiment that's been set up for us. We're going to look at a gas that's in a container. I'll give you an example. What would happen if someone took an aerosol hairspray can and threw it into a bonfire? Someone might think, oh, this is funny, this is going to be cool, but this can actually be extraordinarily dangerous. Because if we look at our data, as the temperature is going up, the pressure exerted by that gas is also going up. What do you think is going to happen? The gas that's in that container is going to build up so much pressure that eventually that can is going to explode. There could be a lot of damage done, so that's a very dangerous thing to do. So follow along as we plot the data on this graph. Looks to me like this is a nice straight line. Do you notice anything strange about it? Is there anything wrong with the graph that we've created? One of the things we talked about with good graphing was the idea that make sure your data points cover as much of the x-axis as you can. And it does seem like we've covered a very good portion of our x-axis. But look at your y-axis. Have we covered the majority of the y-axis? No, not at all. In fact, our data points are all wedged in between a very, very small range. So this is not the best possible graph. It's not the greatest graph for analyzing. So I'm going to show you something else that you can do. Watch what I've done on the y-axis with the increments. You'll notice down on the bottom, I've created what we call a breakage. It looks like a zigzag. What this allows me to do is to start the y-axis not at 0, but at some other value that I think is going to give me a smaller range to cover the data from the data table. So I decided that I'm going to start off with a value of 0.9. And as we count up, every 4 boxes is going to be worth an increment of 0.05. That's tiny. So now look what happens when we plot our data. Notice how we're covering most of the x-axis for temperature and most of the y-axis for pressure. We've got a really nice graph now. We go ahead and take out a ruler and draw a nice straight line and start analyzing this graph. Tell me about the relationship between temperature and pressure. Can you tell what's happening as we move from the left-hand side to the right-hand side? Well, I can tell that the line is definitely increasing. Looks almost like we're going up a mountain. We call that a positive slope. That also means that as temperature is increasing as we go in this direction, that our pressure is also going up. And remember, we call that a direct relationship between the temperature and the pressure. One of the cool things that we can do with the graph is find out information that we might not have known before. We're going to use the data that we've got and find out something that we're looking for. So here's a question for you. It asks, what pressure is exerted by this gas when the temperature of the gas is 16 degrees? I'm going to go down to a temperature of 16 down on the x-axis, and I'm going to take that line straight up until it hits the line that we created for this graph, which is right about here. As I take that over, I can find out that the pressure that's exerted is whatever we would read on the y-axis right here. So I want you to think about it. We said that the difference between 0.95 and 1.0 is 0.05. Okay, and where this is on the graph paper is about midway from 0.95 to 1.00. So I'm going to say that the value right in between 0.95 and 1.00 is about 0.975 atmospheres. That's about halfway from one increment to the next increment. Here comes another question that we can answer from the graph. When the pressure of the gas is 1.075 atmospheres, what would the temperature of this gas be? All right, so we're going to go back to the graph. We're going to find out on the pressure axis, we're going to find 1.075. So that's about here. I'm going to take that all the way over to that nice line that we created, and I'm going to take that down to our x-axis, and it looks roughly like it would be about 48 degrees Celsius, maybe 47 degrees Celsius. So I'm going to put on there that this is about 48 degrees Celsius. So what we're doing is we're using the line that we created to answer questions about things we want to learn. There's a fancy vocabulary word for this, and it's called interpolation. And the definition of interpolation is when you estimate the value in between 2 points. Now I'm going to challenge you a little bit more. Here's our third question. What is the pressure exerted by the gas when the temperature is 56 degrees? 56 degrees on the x-axis. I'm going to do my best to try to take this up to the line, and whoa, wait a second. Our line does not extend that far. Well, what am I going to do now? If this is the relationship between pressure and temperature, we're going to assume that that relationship is going to continue as the temperature increases beyond what we had graphed. So now going back to that 56 degrees Celsius in temperature, I'm going to take it up to the line. And once I hit that line, I'm going to do my best to take it all the way over to the y-axis. Now I'm going to guess that next value is maybe 1.15 atmospheres. Okay, let's go on to another question. Question number 4. What is the pressure exerted by the gas when the temperature is -8 degrees? So let's go down to our temperature on the x-axis, and wait a minute, our very first value is 0. How are we going to go into the negative temperatures when we don't even have graph paper there? Well, we're going to have to try to extend it. If we kept going in this direction, we know that we'd start getting into the negative temperatures. Let's make this a little bit easier on you, and I'm going to add some graph paper for you. Like we said before, even though our data stops here, why not just continue the trend in that same direction? And now we understand that each box represented 4 degrees Celsius. So that first box will be -4, the next box will be -8. And so the question asks you, well, what's the pressure going to be at -8? So I'm going to take that -8 right here, and I'm going to go up to the line. When it hits that line, I'm going to bring it over to the y-axis, and it looks like we're right at 0.90 atmosphere. So this is pretty cool. We're using the graph that we created to find out information that actually is beyond the data points that we graphed ourselves. And again, there's a fancy vocabulary word for this. It's called extrapolation. And extrapolation is when you estimate a value by extending the graph. And that's how you can remember that word. Extending the graph is something you have to do to figure out the answers to the questions. One more really important thing that you need to understand about graphing is slope. Slope describes the steepness of a line. I want you to think about a mountain and think about how steep is the incline of this mountain. So if I was a cyclist, I could measure the incline. You can tell as I go from left to right, it's going upward, and we'd say that that's a positive slope. Well, look at this poor guy trying to go down a mountain in the snow. Well, you can tell that the incline here, as you go from left to right, is actually decreasing. That's a negative slope. And then there's this cyclist. We can tell that this biker is very happy to be driving on nice flat land. There's no incline whatsoever. We would say that there's no slope or zero slope to that line. When you analyze data using a graph, it's an important skill to be able to calculate the slope. How do you do that, and why do you do that? That's what we're about to talk about now. It's mathematically telling you how is the y-axis changing as the x-axis is changing. So we've got this nice green car, and this green car is traveling down the expressway, and we decide, just for the heck of it, we're going to write down how many miles this car has gone after a certain number of minutes. And we collect some data, and we plot the data, and it looks like this. Look at that beautiful line. You can tell that this is a straight line. It's a direct relationship. As time is increasing, the distance that that car is traveling is obviously increasing. But believe it or not, the graph can tell you more information. To understand how to get that information from the graph, you've got to know a few simple things. You've probably seen this equation for a straight line somewhere in math class. Y equals mx plus b. Just a few reminders that b is your y-intercept, and this is where your line hits the y-axis. Well, this is really easy. This hits the y-axis at the origin. That means the distance is 0. So if we were looking at the equation for this line, it would actually become y equals mx, because the b is going to go away. It's 0. So what else is important in this equation that we have to understand? This little m right here, that's the slope. That's the steepness of the graph. Some people will describe slope as rise over run, a comparison of the rise on the graph versus the run on the graph. But what does that really mean? Well, here's what I want you to do. I want you to look at the green line that we've created, and I want you to find 2 points, not necessarily our own data points, but just 2 spots on that graph that appear to be going right through the crosshairs or right through the intersection of the increments. So I'm going to pick this point right here. That one looks like it's going right through the crosshairs. And then let's look for another one. This looks like another good point. Notice I didn't pick data points. I'm just picking 2 random points on the line that I felt went right through the crosshairs. All right, so I'm going to symbolize those 2 points with yellow squares. So what is slope when we talk about rise over run? Well, let's look from the left-hand side to the right-hand side. That's always important to remember when you're calculating slope. The first yellow square, let's label that number 1 or data point 1, and let's label this one data point 2. When it comes to rise, what I want you to think about is the vertical. What is the difference between these 2 points vertically? So to do that, you're going to maybe have to slide one of these over to get a better look at it. So I'm just going to slide this square over a little bit and say, okay, it's right underneath that other dot. Now, as I go from one square to the other square, what's the difference between those 2 values? That's what we call our rise. Now what about the run? Well, we're going to do something similar. We can take that data point 2 and drag it down again and put these side by side and say, all right, what's the difference horizontally between data point 1 and data point 2? And we call that difference in the x-axis the run. So what we want to calculate is the rise versus the run. Looking at this mathematically, let's take data point 1 and drag it over to the y-axis. And we're going to say, well, the value of that is about 40 miles. Well, how about data point 2? Let's drag that over to the y-axis, and you can see that that is 64. So to calculate the change in the y-axis, we take y2, which is 64 miles, and let's subtract y1, which is 40 miles, and we get a difference of 24 miles. So vertically, there's a difference of 24. We're going to do the same thing with the horizontal. When we drag data point 1 down to the x-axis, we find that the value here is about 1.4. And then when we drag data point 2 down, we have a value of about 2.2. So mathematically, when we take x2 minus x1, we get a difference of 0.8 hours. So now calculating the slope becomes very easy. We're going to take the change in the y-axis, which is 24 miles, and we're going to divide by the change in the x-axis, which is 0.8 hours. So the comparison of the 2 is 30 miles per 1 hour. Now think about it. What do those units really mean? This car is traveling 30 miles per hour. Using slope, we figured out the velocity of the car. Not just the relationship between distance and time, but the actual velocity of the car. Now, looking at another graph, we're taking 3 cars, a blue, a green, and a yellow car. And we're going to plot distance versus time for all 3 of them. You can tell because there are different slopes or different steepnesses that the cars are traveling at different velocities. Our green car is going 30 miles per hour. If we calculated the slope of the blue line, which has a steeper incline, it's 55 miles per hour. And the yellow car is only going 15.6 miles per hour. So what we're finding out is the slope can give us useful information. Depending on what you're graphing, you always are comparing the change in the y-axis to the x-axis. Every graph can give you something different.